Okay, so this is a walkthrough of Physics P1, June 2013. Okay, so remember for your physics, you're going to get the equation sheet. So it says on here, it also mentions that you're going to need a ruler and a calculator. So please double check that box before the exam while you're sitting waiting for the exam to start and ensure you've got everything. Okay. Remember that the P1 equation sheet is much smaller than the P2, so you've only got these 5 equations on your data sheet, on your equation sheet for the P1 exam. Okay. Remember that on the front it tells us which answer is going to be marked for prose, so it's going to be marked looking at good English, organising information clearly and specialist vocabulary, and in this paper it's question 4A. Okay, so the rest of the questions, like I've said before, just bullet point, list points, whatever makes it easier, and don't panic about your spelling. Okay, it's question 4A that you need to give a little bit of extra time for planning your answer and making sure it's a sensible answer. Right, so let's make a start. So question 1. The Sankey diagrams show the energy transfers in a traditional coal burning power station and a combined heat and power station, or CHP station. So here we can see we've got input energy from fuel, which is this whole bit here, and then this amount comes off as electricity, but we've got this much coming off as wasted. So we've got quite a large amount of wasted energy there. And the CHP station, we've got the same input, so if you think 1, 2, 3, 4 boxes, okay, larger boxes, that's the same there. We've got some coming off as electricity, some coming off as energy used to heat local homes, offices and factories, and then quite a small amount of wasted energy. So if you compare the two, we can see straight away this has got far less wasted than this one here. What effect does the waste energy from a power station have on the surroundings? So what we should know is that this waste energy will basically just warm up the surroundings. So it will warm it up. Okay, that's what waste energy does, is it just warms up the surroundings. Right, calculate the efficiency of the CHP station using the correct equation from the physics equation sheet. Now the key word here is efficiency. So if we look at our data sheet, we've got 2 calculations that's got efficiency. We need to think about which one we need to use. The difference is this one has energy and that one has power. So if we have a look at our sheet, what's included here, well, it's using the words energy in our Sankey diagrams, so we're going to use this equation here. Okay, so what we want is we want useful energy out divided by total energy in multiplied by 100. Okay, so if we write this down here, so we want useful energy out divided by total energy in. So our useful energy out, and we're looking at the CHP station, we've got all of this here. Okay, so on this side this equates to 100%. Okay, so this would be 100% of electricity going in, and we need to work out what these squares add up to. So we can literally just add up the squares and work it out from that, or we can do it as a percentage. So we've got 1, 2, 3, 4, 5 small squares in each box, larger box. So 5, 10, 15, 20 is our input energy in. And on this side over here, we've got 1, 2, 3, 4, 5, 6, 7 plus 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so what we've got is 16 divided by 20, and that would give us 0.8, and then we need to times that by 100. Remember here on our equation sheet we need to multiply it by 100, and that would then give us 80%. Okay, so 80% efficiency. If you'd left it as 0.8, that would have been absolutely fine. You would have got the marks for that. It wouldn't have been a problem. Or you could have converted it to the percentage as 80%. Okay, right, on to part C. Why is a CHP station more efficient than a traditional coal burning power station? So have a think. So if we have a look, it is much more efficient. There's a huge amount of waste energy here and a very small amount there. So what we can say is that some of the electricity or energy that would have been wasted over here, okay, has actually been used successfully and usefully to heat local homes, offices and factories. Okay, so that's all we're going to say, is that some of the energy that would have been wasted on this side has actually been used usefully on this side. So we have useful or wasted energy, and it's been used usefully. So we can say that some of the energy that would be wasted in the coal burning power station has been used usefully in the CHP station. You could say how, you could say for heating homes, etc. But it's this bit that has been used usefully, it's really important. Okay, a CHP station is usually used to meet the demand for electricity within the local area. The electricity is not transmitted and distributed through a national grid. What is a national grid? Right, the national grid is just the cables and transformers. Okay, it isn't the pylons and it's not the power stations. It's that section in the middle that we're talking about when we talk about the national grid. Make sure you know that's a very, very common exam question. Using electricity locally and not transmitting it through the national grid increases the overall efficiency of a CHP station by 7%. Give one reason why. Okay, so what's happening here is because we're not transmitting it through cables, we're not losing energy as the electricity travels through the cable. So as the electricity travels through the cable, we tend to lose energy as heat energy. Okay, but if we're not putting it through the cables, we're not losing that energy. So we can say there's less energy lost or wasted in the shorter cables. Okay, so it's going through cables, but they're significantly shorter than if we'd sent it through the national grid. Okay, on to question 2. Okay, the picture shows a person taking a hot shower. When a person uses the shower, the mirror gets misty. Why? So if it's getting misty, it's condensation, isn't it? The steam, water molecules in the air are condensing on the mirror, and that's why we're getting it as misty. So we need to now explain that process and why that happens. So the first thing that's going to happen is the water evaporates. So from the shower, the water evaporates into steam. Okay, the water molecules then hit the cooler mirror and lose energy. Okay, it's really important. Remember that if we compare a solid to a liquid, which the molecules are slightly further apart, and then a gas, which they're really far apart, as it goes along here, it gains energy, okay, and the particles have more kinetic energy, can move more. If it hits something colder, it loses that energy from being a steam and it goes back to being a liquid again. And if that mirror wasn't as cold, it wouldn't lose the energy and it wouldn't be converted back into a liquid, okay? So it's this idea of losing and gaining energy which gets it to change from a solid to a liquid to a gas and then back again. So water evaporates into steam, water molecules then hit the colder mirror and lose energy. So the water condenses onto the mirror. Okay, or you can say condensation is formed or something like that's absolutely fine. Okay, so there's our 3 marks for that question there. And again, I've just bullet pointed it, found it easier. There's no marks for putting it into a paragraph, but obviously if you prefer to, then that's fine as well. Okay, 2B. The homeowner installs an electrically heated mirror into the shower room. When a person has a shower, the heated mirror does not become misty but stays clear. Why does the mirror stay clear? So exactly what we just said before. If that mirror is warm, then it won't take away the energy that this gas has here. So it won't then encourage it to go back to a liquid. It's not taking that energy away. So we can say that because the mirror is warm, the rate of condensation is reduced. Okay, and if you want to, you could go and talk about energy, but it's only worth 2 marks. So we're just looking at sort of a basic level of detail here. So we'd say because the mirror is warm, the rate of condensation is reduced. And if you think about your specification, and the videos that I've done that link directly to the specification, it talks about the rate of condensation and evaporation increasing and decreasing, and this is exactly the sort of terminology we need to use in this question. Okay, so you can see why it's so important to look at your specifications. Okay, on to question 3. Okay, question 3. Light waves transfer energy. Complete the following sentence. The oscillations producing a light wave are something to the direction of energy transfer by the light wave. So oscillations just mean movement or vibrations, and you should remember that a light wave is a transverse wave. So it looks like this. So the flow of energy goes in this direction, that is the way the wave is moving. However, the oscillations are up and down, okay? So a fixed point, you'll see it going up and down. Imagine flicking that rope and getting that shape there of the wave. It's going up and down, okay? So the oscillations, the proper word we would use is perpendicular. However, if you described it going up and down, that would have got you the marks as well, but the correct term is perpendicular. Okay, the apparatus in the diagram shows that light waves transfer energy. So we've got a desk lamp with an on-off switch labelled, a solar panel connected to an electric motor with fan blades. Describe how switching the desk lamp on and off shows that light waves transfer energy. You do not need to describe energy transfers. So how can we prove that it transfers energy? Well, I have a clear visual way. If this motor is working because the lamp is transferring light energy to the solar panel, being converted into electricity, if that fan is going round, then it proves that this light is providing energy, or the light waves transfer energy. So we can say if the light is off and no rotation of fan blades, and when on, the fan blades move. Okay, so that, or move, or we can say move faster, depending on if they're going around from the previous time. Okay, so the light switched off, no rotation of fan blades, and when it's on, then the fan blades move faster or go round. Okay, that will prove that it's the light transferring the energy and nothing else. Right, next part. Okay, this question is quite tricky, and you need to, we're often used to drawing a reflection diagram, but not always an image in a mirror. Okay, so a student holds a wristwatch in front of a plane mirror. The student can see an image of the wristwatch in the mirror. The diagram shows the position of the wristwatch and the mirror. So we've got a plane mirror, we've got a wristwatch. Draw a ray diagram showing how the image of the wristwatch is formed. Mark the position of the image. Now this is worth 4 marks. It's quite tricky. Okay, you're going to need to use a ruler. If you remember on the front of the paper, it did tell me that I'd need to use a ruler, so please use one. Right, unfortunately, the only ruler I can find is my daughter's, so this will be the one I'm going to be using for this demonstration. Right, we know that the wristwatch image must be in the same position behind the mirror. So to guide me with this, the first thing I'm going to do is work out where I want the image to go, because that's going to gain me extra marks. So I'm going to measure how far it is behind the line. So we've got about 2.5 centimetres. Then I'm going to put it in the same position behind the line. Okay, so that is where I want my image to go. So as long as I can get my lines to work out correctly, and I'm going to get some extra marks, but I think it is a massive benefit to put it there. Okay, and we can label that as our image, as it's asked us to do. Now we need to draw a rays on. Now what they haven't given you is the eye of the student looking at the image, which is a bit more difficult, so we're going to have to do that ourselves. So the first thing we're going to do is the light, obviously coming off the wristwatch onto the mirror, because that's going to project our image. So we're going to put a light ray in here, and we're going to put an arrow on it. Okay, that's the direction it's travelling. Now we know that this image here, okay, we want it to come down this line, but we also need to ensure that our angle is the same on both sides. Okay, so I'm going to create a line here. Now the examiner is only going to judge this by eye, so if we had a normal line in, they're going to make sure that I and R So this is our angle of incidence, angle of reflection. They are the same. Now they look the same to me. If they were wildly different visually, then you're not going to get the mark, okay? If you want to measure it with a protractor, you can do, but the examiner will only judge by eye. We're going to trace this line back behind the screen, behind the mirror, but importantly, we're going to do it as a dotted line because this is a virtual image. It's not a real image. We're not actually seeing it. Our brain is putting it there, okay? So this is the person's eye here this is the student's eye looking at the image. Now, 4 marks are probably about there. However, I would suggest, because it's worth 4 marks, we're probably going to need to add in some extra rays. So normally we'd see 2 rays coming off, 2 rays bouncing out, and then converging at the image. So what you can do, I'm going to rub out INR for a second for you so it becomes easier to see what I'm doing. Okay, I'm going to take a second line from my image, from my my wristwatch, and then you can see here the point at which is going to converge onto my image, and I'm going to carry on straight down there. Okay, so what's happening is my lines are coming off my wristwatch, they're both reflecting back to the person's eye, and I've created the virtual image back behind the mirror. Okay, so that is what the diagram should look like when you're finished. I've labelled my arrows. Okay, if you want to add in a normal line for both of these, then you can do as well, but there is no need for that. But it would help show the examiner that you understand where the I and the R go and that they are equal. So I think it's good practice to add those in. And we can see the dotted line going back to the image. So that is how you would draw an image in a plane mirror. Okay. The image of the wristwatch seen by the student is virtual. What is a virtual image? Right, you need to remember this definition. A virtual image cannot be formed on a screen, okay? It can only be formed in a mirror, not on a screen. So what is a virtual image? An image that cannot be formed on a screen. Okay, so we can see that question was all about light rays, when we've got a bit about energy in there as well, but then the reflection of and producing an image in a mirror. Right, on to question 4. Okay, on to our 6-mark question in this paper. So in this question, you'll be assessed on using good English, organising information clearly, and using specialist terms where appropriate. Remember, the exam board recommended last year in their feedback that students map out an answer on the back page, roughly, and then come back and revisit this when you've got your ideas in your head a bit clearer. So the diagram shows the structure of a vacuum flask, and here we can see we've got some features labelled, which I suggest are going to be quite important for structuring our answer in the 6-mark question. A vacuum flask is designed to reduce the rate of energy transfer by heating processes. Describe how the design of the vacuum flask keeps the liquid hot, or the liquid inside hot. Okay, so we have got some design features labelled. They have labelled a plastic cap, a double-walled glass container, a vacuum, and silvered surfaces. So I think we should have a paragraph on each, and we're describing how the design keeps the liquid hot. So that's the important bit. Okay, so we need to talk about why the plastic cap keeps it warm, etc. So let's go through. So first, I'm going to bullet point to make it a bit easier, but obviously in the real exam, please do this as a paragraph. So if we talk about the plastic cap and how this helps, this is quite a common exam question as well, so it's worth practicing. So plastic cap, because it's plastic, it's a poor conductor of heat. So we wouldn't want a metal lid because that would conduct the heat out of the liquid much faster. So that's a poor conductor, okay? We can also say that it stops convection currents forming at the top of the flask because the lid is on, so we can't get any convection current going around. So it's a poor conductor of heat. It also prevents convection currents forming at the neck of the bottom. Okay, we can say that the liquid can't evaporate because it's got a lid on as well. So we've got no evaporation of liquid. Okay, so we can see that overall we've talked about conduction, convection and evaporation. Okay, so all really important processes. Okay, and here we can see it's mentioned heating processes in the question. Right, let's talk about the fact it's a glass container now. So the second feature down on the diagram. So the glass container, again, glass is a poor conductor. So we'll use less by the process of conduction. So you can say, so reduces conduction, okay? And that is the main one there for the glass, okay, that it's a poor conductor. So I'll just put conduction, conductor, okay, so reduces conduction. Right, on to the vacuum then, and why that is an important feature. Okay, again, check your spelling on vacuum. It's listed there, so no reason why you shouldn't be able to spell it correctly. So because it's a vacuum, it means that conduction and convection can't happen because they require particles to transfer the energy. And because there's no particles, we're not going to have those. So we can say that conduction and convection cannot occur because they need particles. Okay, so it stops energy transfer, let's say between the double wall. No, it's not in the double wall, is it? Between the flask container. Okay, so between the layers of the container there. Right, and let's go on to silvered surfaces. Okay, the silvered surfaces then feature on this layer here where we've got the vacuum, so that edges of the container we just talked about. Okay, so we have to think about why silvered surfaces, light and shiny, might reduce heating processes. Okay, so what they are going to do, if you remember from the first part, they're going to reflect infrared radiation. Okay, so then we're going to back, if you like, into the liquid. It's going to reflect the infrared radiation, and we also know they are poor emitters of infrared, so they're not going to absorb it, okay, because they're not going to be able to emit it. So we get all of the infrared reflected back towards the liquid. So reflected infrared radiation, poor emitters of infrared, so let's put most of the infrared radiation, which will be heat, is reflected back towards the hot liquid. Okay, so we've covered all the points there in terms of the design. We've talked about plastic cap, glass container, vacuum, silvered surfaces, and we've talked about the processes. So we've talked about conduction, convection, radiation, evaporation. So the clue was in the question in terms of how we wanted to word it. Okay, but it is a common question, this one, showing you a flask and then asking you to talk about it. So it's one worth recapping or going over processes if you're not familiar. Right, on to part B. So we've got Arctic foxes live in a very cold environment. Arctic foxes have small ears. How does the size of the ear help to keep the fox warm in a cold environment? So again, a little bit like biology, make sure you know what the question's asking you. So it's mentioned small ears, but it's asked us how they're going to help keep the fox warm. Okay, nothing to do with predation or anything else. It's about keeping it warm. So the fact they have small ears, so small ears means a small surface area. So what we're going to do is reduce the amount of energy transferred from the fox to the outside. Okay, so we can say, so therefore reducing energy transferred to the environment. Okay, so we talked about small surface area and transfer of energy. Right, on to question 5. Okay, so on to question 5. An electric immersion heater is used to heat the water in a domestic hot water tank. When the immersion heater is switched on, the water at the bottom of the tank gets hot. So we've got cold water in, we've got an electric immersion heater, a copper wall, and then hot water at the top. Energy is transferred by the process of convection from the hot water at the bottom of the tank to the cooler water at the top. Explain how. So what we're doing is we're explaining the process of convection. So the cold water is coming in and it's getting heated by this electric immersion heater. So the first thing we want to say is that the water particles or molecules, whatever you want to use, gain energy. Okay, so if they gain energy, they're going to move faster and further apart, and that's going to cause the water to become less dense. Okay, so it's the idea of getting energy, having more kinetic energy, and moving further apart and becoming less dense. They're going to gain energy, move faster, further apart, and become less dense. Okay, and because of that, so as they are less dense, they will rise in the tank. Okay, and that is how it's going to go from the bottom to the top of the hot water tank. Okay, it is worth 4 marks. There's quite a fair amount to tick off there and might get written in your answer. Okay, complete the following sentence. The main way the energy is transferred through the copper wall of the water tank is by the process of, so it's going through a copper wall, it's going through metal, so we're going to talk about conduction. Okay, it can't be convection because the particles need to be able to move in convection, and because it's copper, it's a solid, so they're not going to move, so it's conduction. Okay, 5C. The immersion heater has a thermostat to control the water temperature. When the temperature of the water inside the tank reaches 58 degrees C, the thermostat switches the heater off. The thermostat switches the heater back on when the temperature of the water falls to 50. Graph A shows how the temperature of the water inside a hot water tank changes with time. The tank is not insulated. So here we've got temperature of water in degrees C and the time in hours. So we can see that just after over an hour it loses all of that heat from 58 to 50. And then the thermostat switches it back on and we get this repeated cycle. So the temperature of the water falls at the fastest rate just after the heater switches off. Explain why. Well, it's because there's a bigger difference in temperature between the water and the air around it. Okay, so the transfer of energy is much greater, and the majority would have done this as an ICER by judging different temperatures of water and seeing how quickly they all lost their temperature or lost their heat energy to the surroundings. So explain why. Because there is a bigger temperature difference between water and the surrounding air, so the transfer of energy is faster. Okay, so we've covered the points there for 2 marks. Right, another calculation. To heat the water in the tank from 50 to 58 degrees C, the immersion heater transfers 4,032 kilojoules of energy to the water. Calculate the mass of water in the tank, and we've also been given a specific heat capacity of water. Okay, so we're given a fair amount of information there. Use the correct equation from the physics equation sheet. So let's have a look at the few equations we've got. We talked about mass, temperature change, specific heat capacity. So this is the equation at the top we want to be able to use. So the first thing we're going to do is write it out. E equals Okay, so that's the equation we want to use. Now we need to substitute in the numbers we've been given. So we have been told it transfers 4,032 kilojoules of energy. Now, energy transferred, energy is measured in joules, not kilojoules. So the first thing we have to do is convert that. Now, if you forgot to convert it and carried it out, you'd probably lose 1 mark overall. We're going to obviously do this correctly. So 4,032 kilojoules. In joules, we need to times it by 1,000 because it's like a bit like kilograms to grams. So it would be 4032 with 3 zeros on the end of it, joules. That is our energy transferred. So, okay, times the mass, which we don't know, we're trying to find out, times the change in temperature, or C. So this is 50 to 58, so that's going to be 8, times the specific heat capacity, which is 4200. Okay, so we now need to rearrange it. It looks quite complicated, there's a lot of numbers here. So the first thing I would do is leave that as it is, mass times 8 times 4,200. Let's convert that into a single number to make it a little bit easier for us. Then we're going to have to move that onto this side. It's going to become a divide. Okay, so we're going to have 40 divided by 33,600 equals mass. And if you work that with your calculator and divide it, your mass becomes 120 kilograms. Okay, a little bit of a hint in terms of what you need there. You're always given the specific heat capacity, and that's in joules per kilogram degrees C. So that tells you what your units need to be for specific heat capacity. You need your energy in joules, you need your mass in kilograms, and you need your temperature change, okay, in C in degrees C. So it's given the units for the equation there. So normally you're given specific heat capacity, which is quite handy, so you can check the units that you need. All right. Okay, on to part C. An insulating jacket is fitted to the hot water tank. Graph B shows how the temperature of the water inside the insulated hot water tank changes with time. So here we can see it looks slightly different to the spiky one we had before. So the temperature in the water on the side, and this time it's taking just, 3.5 hours to lose that energy. An insulating jacket only costs £12. By comparing graph A with graph B, explain why fitting an insulated jacket to a hot water tank saves money. So if we put them side by side and have a little look at them, we can see that over time we've had to switch this heater on a lot less with graph B, so it's held its temperature for much longer. So we can say that the water stays hotter for longer with the jacket. So we need the heater on for less time. So here it's been switched on 3 times, whereas we only just about need it the second time there. Okay, so that's that first one, and we can say that overall, therefore, we're going to have lower energy bills, so it will quickly repay the cost of this jacket, which is only £12. Okay, so if we jot that down then, so we're going to say that the water stays hotter for longer. That's the first effect of that water jacket. So therefore, the heater is on for less time, and we can say, so they have lower energy bills, which means the cost of the jacket is soon paid for. Or you could talk about payback time, etc., if you wanted to as well, instead of that final little sentence there. All right, okay, on to the next question. Okay, in the UK, over 70% of the electricity is generated in power stations that burn fossil fuels. Explain one effect that burning fossil fuels has on the environment. So probably thinking carbon dioxide here, producing then global warming, but you could have sulfur dioxide and acid rain. Okay, one effect that it's going to produce produces carbon dioxide, which contributes to global warming. Okay, 2 marks. I've talked about what it is and I've talked about the gas itself. Right, give one way the effect on the environment described in part AI, so global warming, could be reduced. Assume the amount of fossil fuels burnt stays the same. So they're not asking us to reduce the amount of fuels burnt. What can we do? Right, you could talk about carbon capture, which I did mention in the revision videos, but I think is probably a less likely answer, but just be aware of that. I think plant more trees would be a good answer here, because they take in the carbon dioxide that's produced. So plant more trees is probably an answer you'd come up with faster than carbon capture, but both would be absolutely fine. Right, electricity can also be generated in pumped storage hydroelectric power station. So this is when we have the dam, and then so if we had a high dam going down a hill, and as the water is released from the dam, it flows down, turns a turbine, which is connected to some sort of generator, produces electricity as it flows down the hill. An advantage of pumped storage hydroelectric power stations is the short startup time they have. What is the importance of short startup time? Well, it just means that we can meet a sudden surge or change in demand that happened all of a sudden. Okay, so it can meet a surge in demand. Right, to give one other advantage of a pumped storage hydroelectric power station, well, the clue is here that we can store energy for whenever we want it, okay? You can also talk about it being renewable as well, because we're using the water, so that would be fine. So we can store energy. That would be one good advantage there, okay? Right, on to the next part. Read the extract below from a newspaper article. In the future, it may not be possible to have constant electricity. Families will have to get used to using power when it's available. In the UK, the proportion of electricity generated using wind turbines is due to increase a lot. Some opponents of wind turbines think this increase will cause big fluctuations in the electricity supply. Suggest one reason why this may be true. Okay, well, can think that obviously wind isn't always there, so the turbines don't generate at a constant rate because wind isn't constant. So we can say that turbines do not generate at a constant rate as wind fluctuates, or you can say about it coming and going, changing, it's unreliable, etc. Between 2002 and 2008, the amount of electricity used for lighting in homes in the UK decreased. One reason why. Well, people are using energy efficient lighting, like energy efficient light bulbs, that would be fine. You could also talk about people becoming more environmentally aware and just switching their lights off. However, if you just put switching your lights off, you would not get the mark because it's not a strong enough answer for the higher tier paper. So I think we can say an increase in energy efficient lighting. Okay, right, on to question 7. Okay, electromagnetic waves form a continuous spectrum with a range of wavelengths. What is the approximate range of wavelengths of electromagnetic waves? Quite a tricky question, this one, and one that does not come up very often, thankfully, but it's this one here, 10 to the minus 15 metres to 10 to the 4 metres. Okay, that's the range of wavelengths. Infrared and microwaves are used for communications. Give one example of infrared waves being used for communications. Well, a lot of you with infrared will probably think about TV remotes. That's what we've talked to you about, and that would be absolutely fine to use that. So TV remote controls. Okay. You could also have had optical fibres or data transmission, but I think TV remote controls is the obvious answer. That's one we've talked to you about the most in the classroom. Right, a mobile phone network uses microwaves to transmit signals through the air. The microwaves have a frequency of 1.0 0.8 times 10 to the 9 hertz and travel at a speed of 3 times 10 to the 8 meters per second. Calculate the wavelength of the microwaves. Use the correct equation from the physics equation sheet. And this is important. Give your answer to 2 significant figures. Please make sure you read things like that, because that's an easy way to lose an extra mark. So rather than getting 3, you might only get 2. So we need to use the one with speed, frequency and wavelengths, this bottom one down here. So we've got V equals lambda. So it looks like that there, but however we need to calculate wavelength. So we need to rearrange this equation. So using the triangle, we've got F, frequency times wavelength at the bottom, and speed at the top, velocity V. I want to find wavelength. It's going to be V over F. Okay, so my speed is 3.0 times 10 to the 8 divided by 1.8 times 10 to the 9. Now initially it looks like not a very nice equation. However, if we just cancel out, we've got 10 to the 8, 10 to the 9. They both go in, leaving 10 to the 1 over, which is just 10. So effectively what we've got is 3 divided by 1.8 times 10, which makes that 18. If you do 3 divided by 18, what you get is 0.166666, but it wants it to 2 significant figures. So I need to round up to that point there, 0.16. The number after it is larger than 5, so it becomes 0.17 meters, and that would get me the 3 marks in total there. Okay, right, on to 7 part C. Some scientists suggest there's a possible link between using mobile phone and male fertility. The results of their study are given in a table. Mobile phone use in hours per day, and the sperm count in millions of sperm cells per centimetre cubed of semen. So we've got 0 going up to more than 4, so increasing the amount of phone use in hours per day, and we can see that the sperm count in millions of sperm cells is decreasing as well. So there's a link between the amount of hours they use their phone and the sperm count in centimetres cubed of semen. The results show a negative correlation. The more hours a mobile phone is used each day, the lower the sperm count. However, the results do not necessarily mean using a mobile phone causes reduced sperm count, suggests one reason why. Well, we don't know anything else, do we? We don't know who they've tested, we don't know their age, we don't know if they're overweight, we don't know if they smoke, we don't know what their diet's like. So we really have not got enough information, okay? So what we want to say is there could be other factors involved, okay? You could have named a factor like stress or overweight, smoking, lack of exercise, being in a hot office, and their age. That would have also got your marks. You could have put other factors, e.g. age or smoking, etc. But you couldn't have put insufficient evidence or insufficient testing of people, because we don't know how many people they've tested, okay? So that's the answer. There could be other factors involved. Right, on to the last question. Okay, question 8. Observation of the spectra from distant galaxies provides evidence to support the Big Bang Theory. Complete the following sentence. Many scientists think that the Big Bang Theory describes the something. Well, they think it describes the origin of the universe, or you could say why the universe is expanding. Okay, so it describes the origin of the universe. And then we had to tick one box to complete a sentence. The discovery of cosmic microwave background radiation was important because it proved the Big Bang Theory to be correct. Well, it didn't. Okay, we don't know it's definitely correct. It just added more evidence. So provided more evidence to support Big Bang Theory. Yes, it did. Proved the universe will continue to expand forever. No, it didn't. Right, 8b. Many stars are part of a binary star system. Binary star systems have 2 stars. So here we see a fixed point and 2 stars orbiting that fixed point, and they're on either side of that fixed point. The visible spectrum from stars includes dark lines. These lines are at specific wavelengths. The diagram shows the position of two dark lines in the spectrum from the Sun. It also shows the same lines in the spectrum from two stars A and B in a binary star system at the same point in time. So we've got the Sun, star A, star B. We've got increasing wavelength. So what we see here is that if it's a large wavelength, so the wavelength has increased, so going and spreading for longer and longer, that will be the red end, and this is the blue end when the wavelength becomes shorter. What is the name given to the effect shown in the spectrum from star A to star? So shown in star A, the spectrum has increased, so increasing wavelength, it's moved along, so it's become at the red end, so it's redshift. Right, if we then look at the next part here, scientists have concluded that the two stars in a binary star system orbit around a fixed point between two stars. A comparison of the spectra from the two stars in a binary star system provides evidence to support this conclusion. Explain how. Now that sounds quite complicated. We've not talked about binary star systems. This is now your A-star question, if you like, on paper 1 and on P1, and it's looking whether you can apply your knowledge. So if we look at the binary star system diagram they've given us, we can see that we've got two stars orbiting around a fixed point, and they're both going in opposite directions at any one point in time. So one will be going away from us and one will be coming towards us. Okay, so we know that things going away and things coming towards. Well, if Earth was over here, that would be coming towards us, and that would be going away from us. But in each case, they're both travelling in different directions. If we then go back and look here, star A looks like it's travelling away from us because it's got red shift, and star B has actually got a shorter wavelength, it's got blue shift, so in theory it's coming towards us. So that's by comparing the spectra, it provides evidence to show that they orbit around that fixed point, because at any one point in time, one star will be going away and one star will be coming towards us. So we can say that star A shows it's moving away from the Earth as it's showing red shift or increasing wavelength, and star B is showing a decrease in wavelength and blue shift, which suggests it's moving towards Earth. Okay, so we've talked about the red shift, we've talked about the blue shift, and we've applied it to the binary star system that they've described in their question. Okay, and that is the end of paper 1.